Again, we'll begin with our summary slide showing all of the topics that we'll discuss in this course. So far, we've talked about solving systems of algebraic equations and algebraic equations of a single variable, and we've in fact implemented some of those methods as we've studied other topics. We've talked about various methods for model discrimination, and in the context of model discrimination, we introduced curve fitting and measures of the goodness of fit. We also talked about Newton and Lagrange interpolating polynomials and splines as methods for interpolating data. And then we introduced several applications of Fourier transforms with respect to interpolation and curve fitting. In the previous chapter, we looked at methods for both numerical differentiation and numerical integration. That brings us to Chapter 7 of the methods text, the subject of which is the solution to initial value problems. Initial value problems can be formulated as single ordinary differential equations with initial conditions. These can be solved using what we call one-step methods, and we will introduce Euler's method and higher-order Taylor methods. Euler's method is the simplest of the Taylor methods. We'll also introduce a class of methods called Runge-Kutta or RK methods. Next, we'll discuss what are called multi-step methods. These include the Adams-Bashforth and Adams-Moulton methods, and their combination can be used to develop predictor-corrector methods. Next, we'll discuss how we can solve systems of ODEs and higher-order ODEs as initial value problems. This will require introducing some concepts around stability and stiff ODEs. When solving systems of ODEs, it's useful to take advantage of MATLAB's built-in ODE solvers. By the end of this chapter, in addition to being able to implement these built-in ODE solvers, you will understand how they work. So what is an initial value problem? An initial value problem involving a single first-order ODE is one for which we know either the value of the dependent variable or one of its derivatives at the left endpoint of the domain. So if the domain here for the independent variable is between x equals a and x equals b, and we know the value of y at a for this ODE, then we refer to this as an initial value problem. We can also encounter initial value problems that are formulated as systems of first-order ODEs. In this case, we have two dependent variables, y and z, and one independent variable, x, and we happen to know the values of y and z both at the left-hand side of the domain over which we're solving the problem. Initial value problems can also be higher-order ODEs. Here's a second-order ODE for the dependent variable y and independent variable x. If we know y and its derivative both at the left side of the domain, then we call this an initial value problem. Now, in many cases that you will encounter, the independent variable is t and not x. Throughout this chapter, in the methods text, x is the independent variable and y is the dependent variable. So we'll use that notation here. But x could be any independent variable. It could be a time variable instead of a spatial coordinate. Many problems of interest to chemical and biological engineers can be formulated as initial value problems. For example, we've seen the question, how does the concentration of A change with time as a reacting fluid flows down the length of a tubular reactor? Well, if we know the concentration of A at the input and we want to know how the concentration of A changes down the axial length of the reactor, then we are solving an initial value problem. In this series of two mixing tanks, we might be interested in how the composition and temperature of the effluent from the second tank changes with time. Questions like this can also be formulated as initial value problems. In fact, our general transport equations for extensive properties are many times formulated and solved as initial value problems. In general, the methods that we will introduce for solving the initial value problems follow the same steps. We begin from some initial condition at which we know the value of the dependent variable, y, and then we numerically integrate by one or more methods that we'll discuss in this chapter to approximate the value of y at x1. Then we use that approximate value of y at x1 and the same method or a different method from the one that we used in step 2 to predict y at x2. And then we continue until we have values of y at each point of interest in the domain until we reach y at b. The methods that we'll study in this chapter can be conveniently categorized as either one-step methods or multi-step methods. And we'll formally define one-step and multi-step methods when we get to them in later videos. The one-step methods, as we said, include Euler's method, higher-order Taylor methods, and the RK methods, whereas the multi-step methods include the Adams-Bashforth and Adams-Moulton methods and their combination and predictor-corrector methods. Solving an initial value problem is illustrated here for this first-order ODE. The actual solution may be represented by the curve shown here. The actual solution is known at the left end of the domain, in this case, at x equals a. We use some numerical method to approximate a solution for y at x1 in step 1. And then in step 2, we use that same method or a different method to approximate the value of y at x2. And we continue to iterate that method until we arrive at x equals b. Notice that our approximate solution may not exactly match the actual solution. This is because the numeric integration of initial value problems is always an approximate solution to the initial value problem. In the next video, we'll introduce Euler's method, which is a one-step method and is the simplest of the Taylor methods.